Good morning, everyone. Good morning. There we go. Good morning, everyone. I'm glad to see how excited everyone is about taking organic chemistry. Yeah, all right. That's the spirit. Keep that up. Anyone scared of taking organic chemistry? I can see it even for the people that aren't admitting it. Don't be scared of it. Honestly, I know it gets sort of a bad reputation. It really, if it helps, I was really horrible at organic chemistry when I first took it. I hated it and convinced myself I just wasn't able to understand it. But I think the benefit of that, at least as an instructor, is I understand why you don't understand things. I'm not one of those people that for me it just clicked right away. So like I get what will be challenging, what will be difficult, and hopefully that helps me better understand what you're struggling with. So I think the biggest thing, and you know, any instructor could say this about any class, which is to not procrastinate, don't fall behind, don't cram. Sure, that's useful advice for pretty much any class if it's possible. But I think with organic chemistry, that's where you can really get into trouble. If you keep up with the material, I think you'll find that it's a very manageable class. It's challenging, but it's definitely manageable if you keep up. If you skip a few lectures and you try and catch up on worksheets and all of a sudden there's all these really crazy sounding terms, like anti-Markovnikov addition reactions and all sorts of weird terminology that you just never heard before, it just sounds incredibly terrifying when really it's describing something that might be really simple. So just try not to fall behind and keep up with things and you should be fine. So I haven't posted the syllabus on our course website yet, but I do have a draft of it up here. I need to exchange one of the TAs, I just noticed. Everything else should be fine. I just want to double and triple check and make sure all the dates are right so that nothing gets confusing. But I'll post this later today. It's got all the discussion sections, but you all already know where you're enrolled. Your TAs will bring printouts. The worksheet is online already, and they'll be posted on our course website. But your TAs will also bring physical copies in case you want to use those. But you're also welcome to work on your tablets. So let's see, I'll take a look at our course website in just a minute. I believe we're on the 9th edition of this textbook. Some magic fairy came here and found the solutions manual and textbook and posted it here on our course website. I obviously wouldn't do that because that's not legal for me to post a free copy of the textbook and solutions manual, but it ended up there, so we'll just leave it. It's the 7th edition. The 7th and 8th are pretty much the same, the problem numbers and everything, but if you have the 7th edition here and the solution manual, you can be sure that the problem numbers are going to match up. If you have a newer version, that's fine as well. I don't have a solution manual for that, though. So let's see, Campus Wire, most of you should have gotten an email. That's going to be the primary form of communication. My email inbox is, I hate it, and things get lost. I hate email more than anything. Well, maybe not more than anything, but it's in my top 5 of things I hate in life. And I do try to answer emails the best I can, but the absolute best way to get a response from me is on Campus Wire. So if it's a personal question, send me a direct message on Campus Wire rather than by email. If it's a course content question, post that to the general forum, and I will either answer it myself or my TAs will, or you can help answer each other's questions. But that is the best way to get a response one way or the other, be it a course content question or a personal question. Again, anything course content, post that on the public forum so that other people can see your questions and the answers. But if it's personal, then you can send me a direct message. So, and oftentimes also my emails are going to spam, even though they're clearly coming from a UCLA email address, which I can't understand why it would be filtering that, but that's another issue. So Campus Wire is definitely the best way to go for that. So you'll see everything that's going to be posted up here, lecture notes. What I do is I post a shell of the lecture notes. You'll be able to see that in just a second here. And we'll fill these in during class. So if you want to copy these down in advance in your own notebook and then fill them in, or if you want to fill them in directly, electronically, print them out, whatever you want to do, I want you to take notes during class because I think that is helpful in you learning the material, actually writing it down as we're going through it. But I obviously don't want you to have to focus so hard on jotting every single thing down that you don't have time to really pay attention. So this is sort of a hybrid between that. Okay, so let's see. Let's go back to the course website. The office hours, TA office hours are posted. Mine are going to be, I have two back-to-back 30A lectures, so I will have my office hours after the second one, which will be from 12 to 1, Monday, Wednesday, Friday. I will add an additional office hour at some point once I determine what works for people. I'm sure there will be a number of people that have class during that time, so I will figure out what people want once people start letting me know, and I'll hold another one. And I could always do an evening one over Zoom if that would be helpful. Let's see. I will post the annotated lecture notes once we get through the full chapter rather than every single lecture. But I will post the annotated copies at the end of each chapter. Let's see, lecture recordings. I did not set up Bruincast. Fingers crossed they will set it up for me, even though I didn't request it in advance. In the meantime, I'm taking a screen recording. So I'll either do that, or if my iPad runs out of memory, then I'll record a Zoom meeting or do something. So make sure you get a recording of one of the lectures for each lecture. But hopefully Bruincast will do the work for me. Fingers crossed. We'll see. Discussion worksheets, answer keys will be posted here. Reaction summary sheets by chapter. I'll talk about that when we actually start going through reactions. It doesn't apply just yet. I'll post some suggested textbook problems in terms of homework. It's nothing I'll collect. I'm not gonna check that you complete any of the problems, but there are sometimes a lot of problems in the back of the book and you won't always have time for all of them. So sometimes I'll just kind of make up a list of the most relevant problems that would be useful. And then you'll have discussion worksheet problems. I give lots of practice problems. So you'll get discussion worksheets, additional practice problems. You'll have more than enough practice problems to keep you busy to make sure that you understand things. Bacon, I'm guessing because this is 30A, nobody has done Bacon yet. Bacon stands for Biology and Chemistry Online Notes. This is our form of electronic homework that you're gonna do. It's meant to be fun. So there's a little tutorial and they'll ask you questions throughout the tutorial, and it's meant to just relate organic chemistry to real life or pop culture or something to make it more interesting. It's meant to be fun. It shouldn't take a whole lot of time. The only thing that you'll be graded on is the questions at the end of the tutorial, not the ones throughout. At the end of the tutorial, they'll give you something called a post-Bacon quiz. It's a few questions, and you'll be scored on that. Don't stress out if you don't know the answer to one of the questions. First of all, I end up dropping your two lowest Bacon scores, so you don't have to get everything perfectly correct. Your lowest two scores will be dropped, and honestly, if it looks like you've done most of the assignments and got most of the points, I'll just give you full credit. So don't stress over the answer to a post-Bacon quiz question. They're meant to be fun. Okay, so then let's go back to the syllabus. And just run through anything else that might be important. We'll have two midterms, they'll both be 50 points. Then you'll have your Bacon homework that will be worth 25 points, and then a final exam, which is 100 points. So I've got the schedule at the bottom here. Again, I just want to kind of double check this. Oh, this is the list of your due dates for Bacon. If you go to learnbacon.com, which should link you to our class, the link that I already have on our course website, it is set up for registration to be free for all of you, so make sure you don't pay for some reason. It should already be set for it to be free. But register for that as soon as possible, because they'll start sending you emails in terms of when the assignment opens up, when the assignment is due. They'll send you lots of reminders. But if you want a reference and you don't get those emails for some reason, they're all here. So let's see. Okay, so here's our schedule. Again, I just want to triple check these dates before I officially post it, but we are scheduled to have our first midterm in class on the 26th of April. We'll have our second midterm on May 24th, and then unfortunately I didn't request a common final in time, so I'll have to write two different finals. So this lecture's final is on Monday, June 12th. Okay, so any course logistics questions that people might have? Nope. All right, well then let's get into the chemistry. Okay, so this first chapter is, technically most of this is review, but technically review doesn't mean that people will actually remember it perfectly, so I want to go over enough of the general chemistry concepts that you'll need for the organic chemistry and stuff that we're going to go over. So it'll be a pretty brief review, and I'll just go over kind of the important things that you'll need to know. So, structure of atoms. Remember, the general structure is that we've got this nucleus in the center that's got our protons and our neutrons, and then we're surrounded by electrons on the outside. And if you look at the periodic table, the way you can count how many electrons something has is just going from left to right. 1 valence electron, 2, 3, 4, 5, 6, 7, 8. So in those 8 columns or groups in the periodic table, which atoms on their own are inherently very satisfied? 8, exactly. And that sort of dictates all of the reactions that we're going to look at and all the rationale behind why reactions work the way they do or why structures would prefer to look a certain way, is ultimately that everything is trying to achieve a full octet of electrons. Granted, there are exceptions to the octet rule, but in general, for most of the atoms we're going to look at, because we're doing organic chemistry, carbon, and we're often going to see bonds from between carbon and nitrogen and oxygen. We're working in this second row, and they always want to achieve an octet of electrons. So that's going to be the driving force for why structures might be stable or unstable or why they react a certain way. Ultimately, it's because all of these atoms are trying to achieve an octet of electrons. They want some sort of full valence shell. So we've got 4 different kinds of orbitals, which you can also point out on the periodic table. Remember, this is our S block. Over here is the P block. And then we're really not going to talk too much about D or F orbitals. They exist, they're important, but again, we're mainly working in the second row, and they're going to have both S and P orbitals. So that's what we're going to focus on primarily for organic chemistry. So if you look at the S block, you go across and you hit 2 electrons. So we have 1 S orbital, and you can have a maximum of 2 electrons per orbital. So once you get there, the S block is full, you move over to the P block. So there are 3 P orbitals, because if you count across, you've got 6 more to account for. So there are 3 orthogonal P orbitals, each of which can hold 2 electrons, and that's where we get the full octet from. So an S orbital is spherical in shape, and our P orbitals, look like these sort of dumbbell shapes. We're going to have one, the px, which is in the x-plane, and then we'll have py, and then it's going to be a little hard for me to draw this, but we'll have one also in the pz. And I'm going to look a little more about those orbitals, what they look like, how they overlap to form bonds, and even something called hybridization. When I draw out those orbitals, people tend to totally freak out because I'm drawing hybrid orbitals and I'm showing how they overlap and what it looks like when they overlap and form bonds. But I'm not really going to ever have you draw out those cartoon diagrams of the orbitals. All that background when I go through it is really meant to serve a purpose for later on when we talk about the alignment of those orbitals and how they control a certain reaction and why it's occurring from a certain direction or in a certain way, and the explanation is based on those orbitals. So when we get there, don't freak out about those. They're really just meant to serve as a basis to explain concepts that we'll talk about later on. So here I just have some electron configurations jotted down. This should be pretty straightforward review from general chemistry. I'm not going to have you write out these electron configurations. I'm just trying to show you how many electrons each of these atoms has. I think a better way to think about it is the way I have it described down here. So in general, like I said just a few minutes ago, atoms are going to tend to want to react in a way that they can achieve an octet of electrons. That's going to be their driving force. A lot of times people are looking at reactions and thinking about this atom bonds to this one or this one goes here, but ultimately the thing that's dictating the way atoms are going to bond together or break bonds or change their bonds in some way ultimately has to do with electrons. It's entirely based on their electron configuration and what they're trying to achieve. So atoms are generally going to react in a way to achieve an octet of electrons. And there are several different ways that we can imagine that this would happen. So let's take oxygen, for example. Oxygen has a total of 6 electrons. So if we just think about how we could achieve an octet, one obvious answer is to say it can just gain 2 electrons. Another way you could think about this is, what if oxygen lost 6 electrons? If it lost 6 electrons, then it would go back to that core helium shell, and it would still have that full, maybe not octet in that case, but it would have a full valence shell. So you can imagine achieving a full valence shell, maybe that's a more general way to say it, by either gaining enough electrons to fill the one that you have, or losing all the electrons you have to go back to the previous one, which is therefore full. And then there's a third way, which is simply by sharing electrons. So if you share electrons with another atom, then you can be surrounded by 8 electrons without having to necessarily fully gain or give up any electrons. So we could gain electrons to achieve an octet or a full valence. We could lose electrons, or we could share with another atom. So fully gaining electrons or fully losing electrons, that's more the scenario you have when you form an ionic bond. And when we have covalent bonds, that's more what we're looking at with number 3. When we form covalent bonds, it's 2 atoms that are coming together and sharing their electrons so that they each are surrounded by an octet instead of having an incomplete octet. So that ties nicely into the types of bonding that we can expect, because I just talked about how 1 and 2 are more related to the formation of ionic bonds versus number 3 being covalent. So a covalent bond is formed by the sharing of electrons between 2 atoms. So that sharing doesn't have to be equal. If it is equal sharing of electrons, meaning one atom isn't tugging more on the electrons in that bond than the other, that's considered to be a non-polar covalent bond, meaning it's not polarized with the electrons hanging more towards one atom compared to the other one. Then we can have polar covalent bonds, where there's still some sharing of electrons between those 2 atoms, but one is tugging on them a little bit more tightly, so the electrons in that bond are sitting a little bit close to one atom compared to another. And then finally we have an ionic bond, which isn't a bond in the way, so let's take sodium chloride, for example. We know sodium chloride is an ionic compound. So when we draw sodium chloride, we either write the formula like this, not with an N, or you could draw it as its 2 respective ions, which is Na plus and Cl minus. But what you wouldn't want to draw is something like this. That's technically not correct. When you draw a line bonding 2 atoms together, it's implied that that is a covalent bond. It could be a polar covalent bond or a non-polar covalent bond, but nonetheless it's some form of a covalent bond. When you have an ionic bond, what's happened is sodium, which initially had 1 electron, and chlorine, which initially had 7, just based on their positions in the periodic table, they have a really huge electronegativity difference. Chlorine is highly electronegative, and sodium is highly electropositive, or not very electronegative. And because they have such a huge difference, what happens is sodium simply gives up its electron to chlorine altogether, which is what leads it to become Na plus. Chlorine gains that electron, which is what leads it to being Cl minus. And now what you simply have is an electrostatic attraction. You have a plus and a minus, and they stick together solely based on that charge. So there's a full exchange of electrons. So we will see examples of that, but more commonly, at least in organic chemistry, we're going to be looking at covalent bonds. And then I've got the electronegativity trends here to help you understand whether a bond is going to be ionic or covalent. So the general number you'll find is when the electronegativity difference between 2 atoms is greater than 1.7, that's going to lead to an ionic bond. So there's such a huge electronegativity difference that one really wants the electron, the other one is very willing to give it up. They exchange an electron, they form 2 ionic species, and then that charge holds them together. We're going to be looking more at the covalent bonds. So here, when the electronegativity difference between 2 atoms is less than or equal to 1.7, that leads to some form of a covalent bond. But then we have 2 different kinds of bonds, or covalent bonds, nonpolar and polar covalent. So nonpolar covalent is defined as when the electronegativity difference is between 0 and 0.4. So 0.4, there's still some difference in electronegativity, but it's not significant enough that there's a huge difference in where those electrons sit in terms of the bond between the atoms. They're sharing those electrons relatively equally, not perfectly equally at 0.4, perfectly equally at 0, but they're still relatively in the middle of those 2 atoms between the bond. And then when that electronegativity difference is greater than 0.4, but still less than 1.7, so that it's still covalent, That's what we call a polar covalent bond. And that's what leads to something called partial charges. And partial charges, you'll see they're commonly denoted with this lowercase delta, delta minus, or delta plus. So those aren't full formal charges, but those are meant to show, and you don't always have to draw partial charges. You'll see times when I draw them to explain why a reaction is happening, but it's useful to understand where those partial charges might be. If you have a formal charge on a structure, you always have to show that, but you don't always have to show partial charges. They're really just for convenience of understanding. So I'm going to give you a few examples down here. Actually, let me just look at the electronegativity trend really quickly. So the electronegativity trend goes from the bottom to the top right. So that's increasing electronegativity. So if you think about why that trend is what it is, well, first of all, there's two trends. If I have a trend that's going diagonally, that means there's a trend going from left to right, and there's a trend that's going up and down, and they're combined into that diagonal line. So as you go from left to right, why would electronegativity increase in that direction? Yeah. Yeah, exactly. We've got more protons. So we have more plus charge in the middle that's going to be more tightly holding on to those electrons and trying to gain electrons more. And then what about as we go up and down on the periodic table? Because the other trend to lead to that diagonal would be that as you go up, the electronegativity is increasing. Yeah. Yeah, I think you could say it that way. It ultimately has to do with the radius, right? If you're at the bottom, the radius is getting larger and larger and larger because as you add electrons, you have to keep adding shells. You have to go to 2p and then 3p and then 4p, and you have to start adding d orbitals. So they're getting farther and farther and farther away from that nucleus. So the farther they are away from that nucleus, the less they're being tugged on by that positively charged nucleus. So for those smaller atoms, those electrons are very close to the nucleus, so they're being held on pretty tightly. So that's the explanation for that trend, but ultimately you just want to remember bottom left to top right, electronegativity is increasing. A really quick way to know if you have an ionic bond or a covalent bond, rather than going and looking up electronegativities and doing the math, not that it's difficult math, but having to look up the electronegativities, an easy way is to just say whenever you have a metal bonded to a non-metal, that electronegativity difference is going to be significant enough that it will lead to an ionic bond. So the metals that we're going to be dealing with most commonly will be the metals in the S block. Of course, we have metals that are in the D block of the periodic table, and we'll see some of those occasionally, but typically I'm looking at things like sodium, potassium, lithium, magnesium, things like that. Any of those bonded to a non-metal, which is most of the P block elements, that's going to lead to an ionic bond. So if you have two non-metals bonded together, that's typically going to be a covalent bond. So you don't always have to really calculate these electronegativities. That's a much easier way to figure out if it's ionic or covalent. Okay, so what I want to do now is compare the bonding between lithium, fluorine, versus carbon and fluorine. So I'm looking at their electron configurations up here. If you look at lithium, it has exactly one valence electron. What do you think the easiest way in general is going to be for lithium to achieve a full valence? Bond to fluorine, but if you just in terms of the electron count, it has, it's got one electron, just lose it. So it has to be bonded to a nonmetal for that to actually happen because it can form a covalent bond. But one of the easiest ways you could imagine lithium achieving that full valence shell would just be to lose an electron. And then you look at fluorine on the other end of the spectrum that is exactly one electron short. It would be really easy for it to just gain one electron. And in fact, if we're looking at the bonding between lithium and fluorine, lithium is a metal. Fluorine is a nonmetal. So we should assume that is going to form an ionic bond. So when lithium and fluorine bond to each other, we don't draw this because that represents some form of a covalent bond. Instead, what's going to happen is lithium is going to give up an electron and become positively charged. Fluorine is going to in turn gain that electron and become negatively charged. And then you're going to have that ionic bond there. And again, ionic bonds we don't show by way of a line. Okay, let's compare now carbon and fluorine. And we could also do lithium and carbon. It would give us the same result. But let's look at carbon and fluorine. When carbon and fluorine form a bond, carbon has 4 valence electrons. So how many bonds would carbon want to form to achieve an octet? Yeah, it wants to form 4. So if it forms 4 bonds, then in terms of the octet rule, it will see 2 electrons in each of those bonds, and that will amount to an octet for carbon. So carbon and fluorine are both nonmetals, which means it's not going to form an ionic bond. Instead, 4 of these fluorine atoms. Do I have to draw 4? Are going to form a covalent bond by sharing these 2 electrons, these 2, and these 2. So we're going to end up with something like this. And so now, surrounding each electron, since there's 2 electrons in a bond, all the atoms in that structure see an octet of electrons, so they have an octet of electrons, even though they are sharing. So that brings us down to this part, which is, again, this desire to achieve an octet of electrons surrounding each atom, or at least a full valence shell, is going to be the driving force for how many bonds it wants to form. So if we look at, I'm going to come back to boron because boron's sort of a weird one, but let's start with carbon. It has 4 valence electrons based on its position in the periodic table. So the number of bonds it wants to form to achieve an octet is going to be 4. So it's going to form 1 bond. I'm just going to draw a generic atom, 2, 3, 4. So when carbon has an octet like that and has 4 bonds, it has no lone electrons around it at all. How many bonds would nitrogen want to form to achieve an octet? It has 5 currently. 3. Exactly. It's going to want to form 1, 2, 3, and whatever this generic pink sphere is donating 1 electron into that bond. Nitrogen is donating the other one. So when nitrogen is neutral and has a complete octet, it has 3 bonds and it has 1 lone pair. We'll look at oxygen. It's going to want to form 2 bonds to achieve an octet. So when oxygen has a full octet and it's neutral, it has 2 bonds and 2 lone pairs of electrons. And then finally, fluorine, or really any of the halogens, they're going to want to form 1 bond. And when they do, they'll have 3 lone pairs left over on the halogen. So it might seem like I'm going through this kind of exhaustively in terms of how many lone pairs and bonds and all that, but we're going to be dealing with carbon, nitrogen, oxygen, hydrogen over and over and over and over and over. These are going to be the atoms that we see all the time. So I want you to be able to look at those atoms and immediately know what they should look like, how many bonds they want to form, and how many lone pairs they should have, and what their charge should be when they're in that state. And so I want to do that in a way that's more friendly towards organic chemistry. So one of the ways you can do that is by going through all these rules of drawing Lewis structures. I don't want you to have to go through an 8-step checklist to come up with a Lewis structure. It's something you should be able to do for general chemistry courses, and you would probably need to do that to draw the proper Lewis structure for something like POCl3. It does take a little bit more effort. But what I want you to do is be able to do this without thinking too hard for atoms like hydrogen, carbon, nitrogen, and oxygen, because we're going to see them over and over and over. So instead of going through this 8-step process and calculating formal charge and all of those things, I want to make this a lot easier in terms of how to predict this for organic chemistry. So I will come back to this and actually go through these rules. You've seen them before if people want, or I can at least do a recording and post it or something like that. But I want to really focus on the atoms that we're going to see a lot and give you a way that's a much, much easier way without having to calculate formal charges or do any of that stuff to figure out what these atoms should look like, how many lone pairs they should have, how many bonds they have, all that kind of stuff. So I'm going to do this for carbon, nitrogen, and oxygen. One quick thing that people may have heard before, I'm not sure, there's something called the honk rule. It's saying that hydrogen forms 1 bond, oxygen 2, nitrogen 3, carbon 4. I don't know that that's a particularly useful thing to keep in mind. If it helps you, that's fine. But you really can just tell based on the number of valence electrons, right? So if nitrogen has 5, it wants 3 more, it forms 3 bonds. That's really where that rule is coming from. Okay, so let's start by recapping the neutral version of carbon. Remember, when carbon is neutral, it's going to have 4 bonds. And it started with 4 electrons. It had to share all 4 to get to the octet, so it has none left. So that's what neutral carbon looks like. We already looked at neutral nitrogen as well. We determined it should form 3 bonds, which would leave it with 1 lone pair left over, and then it would have an octet of electrons. And then we have oxygen. Oxygen wants to form 2 bonds, and when it does so, it has 2 lone pairs left over, and that's its neutral form. Okay, so now I want to think about what these things look like when they have a negative charge and what they look like when they have a positive charge, because instead of having to go through and calculate the formal charge, I think there is a much easier way to think about this. And I'm really dragging us through this for carbon, nitrogen, and oxygen because, again, this will make your life a lot easier. From now until the end of probably 30C, people will still be making mistakes about how many lone pairs something has or what the formal charge should be, and it leads to massive confusion. So if we can master this relatively straightforward concept, it's going to make your life a lot easier. Okay, so let's take a look at the anionic form for all 3. So let's imagine how each of these could gain electrons. So if we chopped one of those generic atoms off, one of those purple spheres, we know that there are 2 electrons in that bond. So if I were to yank off one of those purple atoms and take the electrons in that bond and give it to carbon, nitrogen, or oxygen, that's the way that it's going to work to get to its anionic form. We're going to talk about that more specifically in terms of reactions and how that would happen. Atoms don't just fall off and give electrons away. There are mechanisms by which that occurs, but I just want to theoretically talk about how these things get to their anionic or cationic form. So if you imagine chopping off one of the purple spheres from each one and taking the 2 electrons in that bond and giving them both to carbon, nitrogen, or oxygen rather than that purple sphere, that would mean now carbon has a lone pair of electrons. Now, you can tell by the column I'm in that there is now a negative charge on carbon because I'm calling it anionic. But the reason for that is when it's neutral, it has 4 bonds and no lone pairs. It's sharing all of the electrons. Now I went from sharing electrons in a bond to giving both of those electrons to carbon. So carbon is gaining in the number of electrons it actually owns. It's got an octet in both cases, but in the middle case, it was sharing 2 of those electrons. In the case on the left, it owns both of those electrons entirely. So that's why it's going from a neutral formal charge on carbon to a negative formal charge. Okay, so let's do the same thing for nitrogen. If I yank off one of those purple atoms and I give both of the electrons to nitrogen, how many lone pairs will nitrogen have now? And what will its formal charge be? Yeah. So it was sharing electrons in 3 bonds and it was neutral. And now one of those bonds is gone and it owns that lone pair of electrons all to itself. So it's going to a more negative charge. Okay, same thing for oxygen. If I yank off one of those purple atoms, it's now going to be left with 1 bond, 3 lone pairs. And again, it's taking on a negative formal charge. So instead of sitting there doing that formal charge calculation of how many bonds and lone electrons and subtracting that from its valence number and all that, this is just a much simpler way, I think, of doing this without having to do that calculation. Okay, so now let's look at how to form the positively charged species. So the way that oxygen and nitrogen form their positively charged species is a little bit different from the way carbon does it. I guess let's take a look at carbon first because that goes a little bit more with the trend of what we did for the negative charge. If I were to pull off one of those purple spheres, but this time instead of giving the electrons in that bond to carbon, I give it away to that purple atom. So now carbon doesn't have those electrons at all. It's got 3 bonds, but it no longer has that lone pair like it did on the left because I gave the electrons in that bond to whatever that purple thing was. So what's the charge on carbon now? +. Exactly. We're going to talk a lot about whether or not a structure has an incomplete octet. There's one really, really easy way to know if a compound has an incomplete octet. Plus charge on carbon specifically. When you see a positive charge on carbon, you're looking at a structure with an incomplete octet. If you have a positive charge on any other atom, that's usually not going to be the case. 100% of the time, probably for this class. It's not that they don't exist, but for our purposes, if you're ever evaluating something based on whether or not a structure has an incomplete octet, just look for a carbon with a plus charge. That carbon with 3 bonds, the only way for it to get to a positive charge is by simply giving up the electrons in that bond along with the atom it was bonded to. And then it has an incomplete octet. And we're going to use that to evaluate the stability of structures quite a bit. So that's an important thing to be able to recognize. So we could do the same thing with nitrogen and oxygen. I could pull off one of the purple atoms, take the electrons in that bond, have it go away with the purple atom, and they would likewise be plus charged and have incomplete octets. But having an incomplete octet, as we know, is not very stable. There's a way for nitrogen and oxygen to become positively charged without having an incomplete octet. Yeah. Yeah, so they have a lone pair of electrons that they can share. That's the difference between nitrogen and oxygen and what we saw with carbon. Carbon didn't have any lone pairs of electrons. It's got nothing to share and form an additional bond to become positively charged. But with nitrogen and oxygen, they have lone pairs. So if they take those lone pairs and simply share them with another atom, if you go from owning a lone pair to now sharing it in the form of a bond, you're going to go to a positive formal charge. So you used to own them entirely when you were neutral. If you share them in the form of a bond, now you're going to have a plus charge. So for 30A, for probably the whole 30 series, the way nitrogen and oxygen form a positive charge on them is by taking their lone pair and sharing it with some new atom. I'm going to draw it in a different color. And sharing that to form a bond. So now it went from owning a lone pair of electrons in a neutral state to sharing that with some other atom. That's going to give nitrogen a +1 formal charge. So yeah, I can draw it in a way where I yank off one of the purple atoms and create an incomplete octet, but because that's a far less stable species and there's a way to get to a plus charge in another way that does have a complete octet, this is going to be the way that nitrogen and oxygen react. So oxygen can do the exact same thing. It can share one of its pairs of electrons. It's going to leave it with one still sitting there. And now if it went from owning 2 lone pairs to now only owning one all to itself, again, that creates a +1 formal charge. Oxygen in theory could share its other lone pair, but that would lead to a +2 formal charge. Usually you don't get to multiple charges like that. They're usually not very stable. It's possible, but we're not going to see anything like that. So I know this table may have seemed a little bit boring, maybe obvious to some of you, but I can tell you that this, if you understand this table, it will make your life a lot easier. You'll know immediately that if you're trying to recognize a structure that has an incomplete octet, you're just looking for a plus charge on carbon. If that plus charge is on nitrogen or oxygen, it's got a complete octet because it arrived at that positive charge in a different way. So if you can draw these out without thinking about it too hard, again, it'll just make things a lot easier and you won't have to go through all of that. So that'll be a lot easier. Okay, let's see. Via CPR, I think I want to come back to that in just a moment. Let me make sure that makes sense. Yeah. I do. I want to get right into resonance. So I'm not trying to skip around, but I want to get to the point where you can meaningfully work on the discussion worksheet problems. The first set of discussion worksheet problems involves taking a Lewis structure, adding any missing lone pairs, drawing resonance forms, and doing what's called arrow pushing to get there. So I want to skip down to this because the information in between is not going to affect your ability to do the part that I'm going to go through now. So who remembers resonance structures? Anyone? Sound at least familiar? Okay, so I'm going to draw 2 additional resonance structures here and here. And so I'm going to end up with a total of 3 structures there. And I'll show you how I actually arrive at those. Are those 3 compounds in equilibrium with one another? Seems logical, right? They're not. This is what makes resonance structures extraordinarily confusing, and people will probably still be confused by what they really are right through to the end of 30C. And it is a really challenging concept to understand. But what resonance structures are is sometimes charges can be moved around throughout a structure, and they don't actually sit on a single atom exclusively, but they're shared among multiple atoms. So instead of a minus charge sitting on a single oxygen, there might be a way to share that negative charge with other oxygens in the structure. Not always, but for some structures that's possible. So what this represents is not three structures in equilibrium, but rather three different representations that collectively as a hybrid describe the real structure. Now, why we don't just jump right to the resonance hybrid, I think you'll appreciate pretty quickly. So let's first start by actually drawing out these other resonance structures. So right now, if I label these as oxygen 1, 2, and 3, there's really no reason why 1 and 2 have to have the negative charge and couldn't be the ones that are pi bonded or doubly bonded to the carbon and be the neutral one. So that oxygen at the top, for example, could be the one with the negative charge. So one resonance structure I could draw would be this. So I'm going to leave number 1 with that negative charge, and I'm going to put the pi bond to oxygen number 2 instead. So if oxygen number 3 had 2 bonds, 2 lone pairs, that's its neutral form. Now it's got 1 bond and 3 lone pairs, that's its negatively charged form. So now that's going to be a negative formal charge up there. And then similarly, I could have the pi bonded oxygen to carbon be oxygen number 1. That would make it neutral with 2 lone pairs. And then the other 2 would have 3 lone pairs and a negative charge. So I could take that first structure and just rotate it to make it look like the other 2, but that's not what these resonance structures are representing. These 3 oxygens are different atoms. And so their ability to share that negative charge amongst themselves makes it so that any one oxygen atom doesn't have to bear that full -1 charge, and instead it can be shared among the 3 oxygen atoms. So the resonance hybrid for this, let's look at all 3 structures. So in all 3 of our resonance structures, if we look at any carbon-oxygen bond, it's either a single bond to carbon with a negative charge, or it's a double bond to carbon with a neutral charge. So what's halfway between there? It has a full single bond in every single case. And then if in one of the resonance structures it has a pi bond, the other 2 it doesn't, then it has in reality just a partial pi bond. And that'll be true of all 3 oxygens. So we use a dotted line to show that partial pi bond. Okay, so then how about the charges? What would be the charge on each oxygen atom? Yeah, so in this case, because all 3 of these oxygen atoms are identical to one another, they're all oxygen, they're all going to want to share that negatively charged exactly equally. So we could here assign an actual number to each of the charges. So what would that numerical value be? So it was -1 in each individual structure. What would the numerical charge be if I had to do it mathematically? Yeah, each one would be -2/3. Do you want to draw stuff like that? No. And this is actually, believe it or not, the easiest possible way to draw a resonance hybrid, because it's oxygen, oxygen, oxygen. They all want to share that negatively charged equally because they're all the exact same atom. You can perfectly split up the charge into 2/3 and represent it that way. But that's not always the case. So if we compare to this structure down here, which is very similar, I have a CH3, here I have a minus charge on this carbon atom. And I could imagine instead of having the pi bond to oxygen and the minus charge on carbon, is I could put the pi bond between the 2 carbon atoms. That would make the carbon neutral. That would break the pi bond on the oxygen and make it negatively charged. I could draw it that way as well. Well, now the resonance hybrids get even trickier, because who prefers to have that negative charge if we had to guess, oxygen or carbon? Oxygen is more electronegative. So we can't just simply split the charge in half and say minus a half on oxygen and minus a half on the carbon, because that's no longer relevant. But we're not going to sit there and do a really formal mathematical calculation about just how much more oxygen wants it compared to carbon. So instead, when we draw a resonance hybrid for something like this, it might look something more like this. And we'll do partial minus on one oxygen and partial minus on the carbon. So that's our shortcut of not having to figure out exactly by how much more the oxygen wants to charge versus the carbon, as we just start to do these partial charges. And then you can see it can be hard to figure out how many lone pairs to give each one when you have a partial pi bond, and how many electrons do you put on things. So it can get really challenging. So I don't think I will ever ask you for a resonance hybrid, which is this and this. But I do want you to conceptually understand that none of these resonance structures individually, none of these exist in that form. Carbonate anion CO3 2- doesn't look like this. It doesn't look like this, and it doesn't look like this. It looks like the hybrid. So it's really important to keep in mind the reason that we draw these resonance structures is because these are nice, beautiful Lewis structures. And the resonance hybrids are disgusting and really difficult to draw. So it is a really hard concept to wrap your head around, that when you draw those three structures, none of them actually exist, that it's a hybrid among them. But that's the purpose of resonance structures. So if we look at this, and I wanted to ask this question a little bit earlier, but that's okay. If I label these bonds A, B, and C, so A is the double bond, B is the single bond in that structure that I've drawn, which of those bonds is longer? And it's sort of a trick question, if that helps. They're all the same, right? This is only one resonance structure. That is, this compound has three, and the real structure is a hybrid among those three structures. So if it's a hybrid among those three structures, it's going to look something like this. And they're all going to have, even if we don't know exactly what it is, we can look it up, all three bond lengths are going to be identical in this case, because they all have one full bond and then one partial pi bond between them. So resonance is always a tricky thing for people. So last thing I want to cover, which will help you a lot with the discussion worksheet, is arrow pushing. So this is going to be a concept we use a lot throughout the 30 series. Arrow pushing is a way to show electron movement. Here we're going to use it to show how we arrive at different resonance structures. After that, and for the rest of the 30 series, you're going to use it for mechanisms to show how an actual reaction takes place, how new bonds are formed, how bonds are broken, and how those kinds of things occur. So it's a really nice place to start by doing these with resonance structures, and it also makes resonance structures a lot easier to get to if you understand what the arrow pushing is. So, quick overview, arrow pushing is used to show the movement or delocalization of electrons. The arrow pushing is also used to show mechanisms, but we'll get to that later. We used curved arrows, meaning it's curved like this as opposed to straight. And I want to reiterate that these are always showing the movement of electrons, not the movement of atoms, and not the movement of charges. If I move electrons, the formal charge on an atom could change. So that can happen. As a result of that arrow, you could end up with a different charge. But you're never going to start an arrow on a charge and show where it moves, because a charge itself isn't electrons, especially not a positive charge. A negative charge isn't necessarily electrons either, but we're always going to start it on a pair of electrons and then move it to some other location. Again, that could result in atoms or charges moving, not atoms in the case of resonance structures, but the arrow itself is showing the movement of electrons only. So let me go back to this structure and show you how I could do the arrow pushing to get from one to the next. Okay, so let's see, I want to get the double bond to that top oxygen number 3, and I'm making a double bond to number 2. So if I start my arrow on a pair of electrons, the lone pair on oxygen, and I land it between the carbon and oxygen, what I'm showing is that I'm taking that lone pair and I'm using it to create a pi bond between those 2 atoms. So sometimes your arrow will land between 2 atoms to form a new bond. Sometimes it will land on an atom to give that atom a lone pair. I'm missing an arrow here though, I need to do one more. For one, I can never have more than 4 bonds around carbon because I can't exceed the octet. But I also know that to get number 3 negatively charged, I want to break that pi bond. So I'm going to take the electrons starting on the bond and give it to that oxygen atom. So that's a case now of starting in between 2 atoms on a bond and giving that to an atom in the form of a lone pair. So that's how we get to this middle structure here. I have a method by which we can rank resonance structures in terms of their stability, but that's not worth rushing through right now. I feel like there was just one last thing I wanted to say before I let you go. No, we'll just stop there. It's already 1 minute after, so I will see you all on Wednesday. And we do have discussion this week, so make sure you go to your discussion section.